So let's start. This way only. Okay. So nice to see you only join us. Hello, and we will start. Okay. The topic of today's lecture, it's mathematical statistical data analysis in medicine, biostatistics methods, and introduction to evidence-based medicine. So in fact, topic very huge, and I will be able only provide some introduction in all this into all these questions. Moreover, I think I will not complete entire lecture, and maybe I will continue some parts next time. Okay, so let's go to main question of lecture's main questions. First of all, as example, I will use Microsoft Excel application. It's not best tool, that's important notification. It's not best tool for statistical analysis, but such as it's widely available and easy accessible, I use this exactly. And actually, if you will get the idea, or maybe already have some experience, definitely I know that somebody of you already have experience with such topics like hypothesis testing, statistical analysis. So it actually does not matter which tool you use. Because here is most important to understand principles, and then we can easily accept necessary approach, necessary tool. So here is anyway reason it will be spreadsheet like Excel, not necessarily Excel. All things that I will talking about will work same way in Google spreadsheet or LibreOffice Calc and so on. Okay, so here is a little bit reminder about features of spreadsheet. That's this part I will pass quickly because it has to be for you now from school, Lyceum or so. And then statistical analysis, correlation, regression, and if we will have time, probably next time, it will be optimal management task example. So here is agenda. And let's start with first question. Actually with some necessary technical background which is required to make not only statistical but any kind of data processing in spreadsheet. So actually as main goal of spreadsheet, digital spreadsheet application, it's to make some calculation. In this case, we need to use formula there. So here is actually general syntaxes, and when we want to create formulas in spreadsheet, we have to follow necessary syntaxes. Here is given syntaxes for simple formula. Here is given example for more advanced formula, and there is no mistake because I just want to sign most like ambiguous and doubts parts of Excel spreadsheet application, fortunately not available in other. So specifically in Excel, some function being translated into different languages, and you can make something like this, where part of your formula will be written in English and part in language which is your computer, your user account configured to. So here is we have, like, again, pass through quickly. We start with equal syntaxes, then we follow body of formula which could be composed of mathematical equation, arithmetical formulas, or function name along with arguments, and we supply data like reference to cell or arrays. So again, I am expecting you already familiar with all this, but anyway, here is now anatomy not only formula, but specifically function in spreadsheet. And here is we have function name, and inside parentheses or brackets, we have an arguments which composed of it might be one or more arguments separated by delimiter. Again, delimiter might depend to regional setting. In this case, it's comma, but it might be semicolon as well. Every time check system hints about active delimiter. And here is we have arguments for this particular formula, arguments supplied as arrays when colon indicates limits, boundaries of array, start and end cell. So in this, again, recap this particular formula, functions, this formula composed by function, some product, which in turn expecting and supplied by two arguments separated by comma, and both arguments represent arrays. So we do operation over arrays. In this case, okay, again, in another example, we have both same case with a function which this time has only single array as argument, and most important things is below. It's so-called array formula. Array formula, it means if we have array of data and we want to process each one value, like adjust each one value, so we can apply array formula at once for entire content of array. And here is we have to use curly brackets to entitle array formula and make, of course, selections for our array. In other things, array formula works very similar way like other. In this particular case, this formula will summarize given array range and then multiply each results by a corresponded constant depending on which row it will be applied. Okay, so again, recap, what could be arguments of function constants, reference to cells, which in turn could be relative and absolute. Actually, references, it's a main way to supply data into your formula. So here is, we have three examples of references. Actually, for example, a conventional example when we refer specific cell, and this reference will be updated when we move around our formula. And with using $sign, we can make strict references to specific cell or column or row. Here is more example about this one. How we work with relative reference when we drag formulates will be updated, or how we use mixed reference or absolute reference for that specific particular cell. Okay, then column and absolute column and absolute row references. Here is given example how it will be look like. So how we can, every time we can move formula along row, and it will be refer the same row number, or along column, and will be refer every time this particular columns. So again, to summarize with arrays and sets as arguments, or ranges in general. So arguments could be range, and we have two types of ranges. Array, when we use colon exactly, and in this case, all in between cells will be used as arguments, and sets when we delimit our arguments by semicolon, and then we will construct structures like this one. So here is, this way we can combine two array. Okay, I think it's more should be enough about introduction to techniques. And finally, I can only talk about assistant, very old tool, equation wizard, and still present even in modern spreadsheet. When you press the fix button, and in dialog mode, you can pick up necessary function and provide arguments. So here is, we have what is benefits. If you're not sure about function name, you make search. You can review list of function by categories, and you can in interactive dialog, you can fill your data by picking it from worksheet. So it's the things you will do on practices, and you already did, yes, of course, last week on your practices. So the only sometimes difficulty we have with this tool, and if you want to create complex formula and make yet another function call from inside existing so-called nested function, it might be a little bit not obvious and a little bit difficult. So I prefer to write equations, formulas directly into cells. Okay, that was, as for me, enough about technical tool. Again, it's corresponded for all spreadsheet except that point about translated function name. It's only a very specific Excel feature. Fortunately, that Google spreadsheet and LibreOffice not inherits this. Now we're starting to deal with main objective of today's lecture, and so we move into statistical calculation by using spreadsheet, let's say. First of all, we were talking about descriptive statistics and definition of statistics in general in descriptive statistics, then move into hypothesis testing, and again back to spreadsheet to point about data analysis add-on, which help with some statistical analysis. So if you talk about statistics, it's defined, it's been seen as a branch of mathematics which deal with collection, organization, analysis, interpretation, and presentation of data. And when we talk about medical statistics, it's of course its application of statistics to medicine and health science, and including epidemiology, public health, forensic medicine, clinical research, and so on. And again, it's already recognized as independent branch of statistical science fields for decades yet. Here is. Also, when we talk about statistical analysis, we very often spoken about probability of something happen, not happen, and so on. So how do they are related together? Because actually probability, it's again independent scientific area under the general mathematical statistics. So if we talk about probability, it's measure of likelihood that even will occur or doesn't occur. And it's studied under probability theory, of course. And here is, they are both statistical probability very tightly related, but separate academic disciplines. In fact, statistical analysis, not often, it's almost always use probability distribution. So we will every time very often refer to probability. And simply a chart below shown what is main objective, what we deal with in both probability and statistics. So the probability, we are given model and we are going to predict data, like when we toss coin, which side we will, let's say, or how many times fair, best, or so. And in statistics, we do exactly opposite side. We already know number of events happen, and we want to get some model from there. We want to get evidence that it's not that we have some mathematical order behind this data. It's not just random variables, random values. Sorry. So that's major difference. Okay. Let's again summarize this. When we talk about statistics, we measure of some characteristics of our data. Here I spoken sample, but it's in fact not exactly true. In general statistics, we measure characteristics of our data set. And this data set could represent or population or sample, depending for circumstances. So population contain all members of group, and sample represent a subset of population. So it could be easily seen like all students in our university represent population of students of Ternopil National Medical University, but your group, it's only sample on the population of students of our university. Again, those definitions will be not strict because depending of, we can make scaling of this term and consider all students in Ternopil or all students in Ukraine or all students in Poland, Europe, around the world. So meaning population might be changed. Again, definition of population and sample in reality will be depend to task you analyze and not very obvious in all cases. So sometimes it's required some little bit thinking to understand what do we have as population in our case and what will be the sample. Both case population samples represented for us two variables or characteristics that can form different value from one observation to another. And we separate those variables into independent and response. So independent variables is measures that can take different value, and it's subject to manipulate by research. So by researchers, so researcher could make changes for independent variable, could make changes for those could have control on this input. For example, is it how it select sample representatives, or is it they were given some specific substances or so. And as a result of manipulation by independent variable, researcher will retrieve some response from another variable which is not controlled but observed during our experiment. And other name, it's dependent variables. So we are manipulating by independent variables and we got some responses, we collect some data, and we are going to make conclusion on this response variable, how like we give some medicine for our patient and we observe changes in their health condition and recording of responses, recording their biological, some vital parameters, vital signs, and then we try to make conclusion about effectiveness, for example, of our new treatment. It's a very common case. Okay, now a quick overview. Again, we're back to mathematical facts of variables. What type of variables do we have? Actually, all so that we can deal with, we can be grouped in two large categories: categorical, quantitative. Categorical could be selected into binary, nominal, or ordinal. And discrete, we have numerical or continuous uninterrupted. Means, what does it means? Let's say binary means we have only two value, like 0, 1, true, false, or something like this. With nominal, we have more categories to classify our data. And with ordinal, we have organized categories by value. So when we talk about discrete value, that could be represented by some discrete numericals, numerical data, numerical measures, or they can have continuous characteristics like some time or blood pressure, which we have every time some value at any smallest fraction of second, of a fraction of time, they are changed itself. Anyway, it's important to understand when we talk about quantitative continuous variable, when we manipulate this data, we deal with recorded fixed data, which in fact will be only discrete. So no matter if originate it's continuous, when we record it, when we make some, put it in some storage, we deal with discrete. Okay, I have already spoken about this, just few examples about categories like treatment groups, exposure group, disease status. Binary have two layers, they given examples. Additional example to those I have provided, like did the live treatment, placebo, and so on. Nominal variables. Here is nominal and ordinal. That's most important, most interesting cases, in fact. In nominal variables, order does not matter, like marital status, blood types of patient, and so on. And ordinal variables, it's ordered categories. When orders matter, we have some development on cancer, birth order, or my favorite example, letter, as well as numerical grades. So these things teacher give for student, like numerical grade. In our case, now in Ukraine, we have from 1 to 12, and then by the end of semester you are you got pass your exam, again got numerical grades, and then got ranking, letter grades, ABC, and so on. So all these grades represent ordinal variables. So even numerical value could be considered as categorical variables, depending to methodology of its usage. So here it's important to understand that even we have numbers, it does not mean that they are that we deal with quantitative discrete data set at all. We have to analyze our variable, we have to understand nature of our variable, and because of this, it's depend what we can do with our data, because some major difference with quantitative and qualitative variables. With quantitative, we can perform numerical or arithmetical manipulation, because like counts, time, divide, and so on. But we can't do it with quality variables, despite, for example, like in case of grades, very popular things to calculate average, but in fact, it's work against nature of this variable, so it's not very correct approach. In contrast, turning numerical grades into rankings, it's do correct approach. So anyway, right now I moved into quantity variables. And here is we have example of discrete numbers and continuous variables. What do we have? Like, so here is major difference for understanding, like numbers of patient in hospital, number of students in universities. That's all things that's discrete numbers, for example. Continuous variables, take any number as definite range, as I already spoken, like blood pressure or age. So any fraction of second we become older, so age is continuous variables. Well, when we talk about descriptive statistics, it's tool to visualize our data. Visualize our data and replace data set with large data set, especially with some brief description of our data. So, of course, first way to visualize our data, and most common, it's depicted in form of chart or graph. And here is in the center main rule. Every time we have to use common sense, we have to thinking about what kind of data do we have and what is actually represent to use appropriate visualization approach. So again, it's not exactly very easy to build chart. Technically, it's very easy to build various chart diagrams with modern application, no matter if we talk about spreadsheet or something like more advanced, like statistical application, SPCC, R, and so on. Technically, usually very easy, but again, we must get some meaningful information, and here is the problem very often. So, quick review. Right now, I will make emphasis not on exact data visualization, not to depict our numerical data, but rather to depict frequency, how data occurs within given case, within given variable. Because if we talk about statistics, if we talk about summarization of our data, which statistics actually do, for us, most important to have not each value depicted, but get some summary from this. And here is fast summary case frequency plot. How often some events occur within our data set. In case of categorical variables, it's useful to have a bar chart or linear chart with various types, like this one. So they will depict currencies per categories. In case of continuous variables, to visualize frequency, usually we use things like stem and leaf plot, box, and histogram. Actually, stem and leaf very rarely used right now, and it's applicable only for very small data set, like given example. But anyway, maybe you will need this. Major approach, it's box plot, of course, and histogram. Sorry. Доброго дня, Аркадій Гаврилович. Перепрошую, трошки лекцію маю зараз з іноземцями, але якщо терміново, то кажіть. Okay, sorry, it was from university authorities call, but not urgent, and we can proceed. So again, major frequency plot for continuous variables is box plot, very useful in case of depicting descriptive statistic parameters. If you already have experience with some scientific article, probably you had seen there such diagrams, and histogram, which are also very good to visualize characteristics of and distribution, specifically distribution of our dataset. Okay. What is actually also very often being used for continuous variable is scatter plot, but it's important to understand that it's not a frequency plot. It's only tool to visualize the data set itself. So here is important to understand these points. Maybe in a few minutes I will show some live example, but right now just this statistical example. So here is we have, okay, case, for example, how we visualize frequency of shock index per patient. So we have levels of shock index, which is again perfect categorical variables, ordered variables. And so such as it's again integer number of cases of this particular shock index. So we have specific number of patients that suffered from this shock index. Okay, it's good to depict it in a form of bar chart, and we have this. In this case, we will have frequency plot, how often patients suffered from particular shock index. Okay, stem and leaf, I already exposed how do we have this, how we made this. Again, useful for relatively small data set here, give an example, and how we put our variables into data. So what do we have and our specific value. Okay, let's move. For me, more interesting is this one. Not sure. Okay, histogram. Histogram depicts depiction of a distribution of continuous data set. So here is we have, in our case, independent variable have to be continuous. Yes, continuous. For example, in this case, it was so arrivals, no matter plane to airport or, for example, patient to emergency department. So we have some particular time when we register new arrivals, moment in time, and depending how we will consider which, how we will split our time in which section, which chunks, is that we will use minutes or two, or 1 minute basis, 2 minutes basis. We can calculate frequency, how many patient or planes or whatever arrives for made arriving within a given time interval. In this case, definitely 1 minute had been used. And here is we have frequency, how often it's happened, how many patient usually arrives, for example, per minutes here. So again, purpose of histogram is to wrongly assess probability distribution of given variable. So how often we depict frequency of observation and according to time range of value. So here is we have, as you can see, we have peak between 3 and 4. Yeah. No, here is half of minutes has been used here. Sorry, I was wrong. 5 years, 30 seconds had been used measure. And here is we have between 3.5 and 4.5 minutes we have maximal frequency of arrival. So right now, let's again recap and finalize what is descriptive statistics. It's summary statistics that quantitatively describe and or summarize features from a collection of information. Well, descriptive statistics, as in the most known sense, is process of using analysis of those statistics. So it's actually what we do and what we get at the same time. We can do descriptive statistics in order to get descriptive statistics. And actually, you should already have completed those part of classes. Okay, and it's distinguishing from inferential statistics or inductive statistics by its aim to summarize its sample rather to use data to learn about populations that as a sample of data to represent. So actually, with descriptive statistics, we describe data we collect to our experiment, and usually we want to use those information which we gain from descriptive statistics to make some induction and summarize our assumption on entire population on different cases. Okay, so what we can do with descriptive statistics, what kind of analysis we can accomplish there. So here is we have central tendency, quartiles, variation, and maybe can make assessment for, central tendency, quartiles, variations, shape, and so on. We have number, and as you can see, sometimes we have number of characteristics, and even this list is not fully completed. Not fully completed, it could be extended. Why do we need so much characteristics? Why do we need this? Actually, it's a problem because it's not easy to really obtain some realistic measures and got some final conclusion. And also, again, our assessment will be depend for our data type again. So we'll again back to that chart with qualitative, quantitative data. And if we can, in case we have interval level data, we usually measure central tendency and variation. So with central tendency depict for us some single attributes of our variable, of our single attributes, single characteristics of our variables. Variation describe how data vary, how describe deviation of data from this central tendency. And we use some synthesized scores which combine both central tendency and variation to a single descriptor. For example, we use mean and standard error, that it's kind of standardized scope. That's which depict mean of our sample, and standard error show deviation from deviation of data from mean. In case of nominal ordinal data, qualitative data, proportion are common methods that describe frequency as they compare to a total. So which percentage from our data set fit in our data? Okay, so what we can, what is major descriptive statistic characteristics, especially talk about central tendency, mean, median, mode, again, must be known from let's say on course about those things. What is mean, how it's calculate, arithmetic average, that's median point of scale is measurable, fit percentage, mode, frequency occurrence, most frequently occurred score in distribution, and so on. Okay, that's theoretically, it's much better to show it by example. We have our variable, we have our scores, x of y items. We have number of scores or sample size or number of cases, again sample size, because in this case we deal definitely with some sample of our person with different age. We have sum of scores, and of course we have mean. And here is we have, such as we have even number of cases. Here is we have clear median, which is divide our data set by half. And here is we have mode. We have two items which is being repeated there. So here is will be mode from our data set. Again, why do we need all this stuff? Actually, here is we have answer, because some of these descriptive statistic parameters could be very easily affected by some extreme values, extreme measures, or maybe incorrect measures like outliers. And here is we have examples that's, for example, mean or arithmetic average very easily could be affected by outliers. And compare, median will remain the same for these two examples. As a result, we can easily determine, first of all, we have chance to made assumption about potential presence of outliers or potential presence of some errors during our experiment. Or if everything is definitely correct, we got evidence that we have some skew in our data. They are non-linear, they have some specific biases inside, which is actually might be nothing wrong because it's like just life. Similar things we have with variation or measure for dispersion. It shows how the information spread or variably of the data value. So here is we have two frequency plot. Again, it's not data plot, it's frequency plot, how often some value repeated in our data set. And those two data sets have exactly the same central tendency. So they will have exactly the same mean mode average. But because distribution of data is different, deviation is different, variation is different. And here is this way we will be able to distinguish our data set and make conclusion without having even this picture. Just by having numbers, we will be able to make conclusions that we have something different with those data sets. Okay, quartiles, also very common measure for assessment. This time we divide our sample population data set into 4 quartiles, and each one represents exactly 25% of our data. And usually we deal with interquartile range to depict, that's half, to depict Q2 and Q3, or mean half of our population belong to, in this case. So of course we use some time range, largest minus difference between largest smallest value, but more information give for us interquartile range, so difference between first and third quartile. So here is this one. And we can compare both range and interquartile range to make assumption about how data being distributed there. Again, interquartile range, it's basis for box plot. Again, here is some formula how to make this calculation and how we can do it mathematically, arithmetically. Of course, it's much easier to be done with. It's much easier to accomplish all this calculation in spreadsheet. Moreover, it could be automated, and we have necessary function to get it instantly in spreadsheet, like in other statistics application. Okay, so here is again why do we need, so how we combine averages and our mean. Here is 3 different data set with 3 different alignment of our data. As you can see, in all cases we have the same mean. Of course, mode and median will be different, but here is also we have different standard deviation. And that's example of standard score. We have mean plus minus standard deviation. So here is we have, like here, data B data set, we have relatively small standard error, standard deviation. So our data is concentrated around the center of our distribution. And here is at A and C case, our data scattered more widely and so greater standard deviation, so more significant set deviation from our central tendency. And actually, as I already said, very useful tool to visualize all this data. It's a box plot chart, which show for us number of descriptive statistics parameters at a time in single tool. So here is we have for us shown median, for us show interquartile range, for us show expected minimum and maximum. Here is we have expect minimum of maximum, which is Q1 minus 1.5 of interquartile range, and real maximum, real minimum, as well as outliers from our expected ideal data set. Okay, so here is just depiction. Should be, as I already said, it's very useful to have spreadsheet application and can give for us some number of assessment at once with various functions, which not all listed there. We have much more function to make calculation of descriptive statistics. Same case, okay. Before we will move into statistical, what is this? I think it's time to move a little bit into our example. So here is we have actually two examples of data. If you notice, you will see exactly the same numerical value, but depending to how we will describe processing of data collection, what it's actually, we will have absolutely in other cases. For example, here as we made observation of two groups of patients and recording from each patient something like some kind of vital parameters. Maybe we observe two patients with some arterial hypertension, that could be blood pressure, or it could be relatively high blood pressure, maybe sometimes deadly, or maybe any other parameters. So here is we have three variables. First of all, it's patient number, or name, and in this case, it will be quality variable. So patient independent variable, it's quality variables this time. And observation itself is definitely look like discrete value. But so independent variable, it's quality nominal, and observation is discrete value. Let's move into something another. We observe two patients, true time, and we made the recording of some their vital parameters. For example, changes of blood pressure with time, for example. No, again, it's too hard. Or maybe ECG, or some any other observation we are going to do. In this case, independent variable, because its time is continuous. Dependent variables is continuous, and again, dependent variables are both discrete. Maybe they are also continuous if we measure, for example, wood pressure or ECG. Maybe they are also continuous. But once we got this set of data, we're talking about discrete set of data. So nature of data is continuous, but recording variables is discrete. Anyway, it's quantity. So in this case, all three variables quantity. And if we talk about depict our data, so of course, if you want to depict, for example, group one, of course, it will be absolutely correct, like I have spoken, it's to use something like, not in this case, such as patient number is, patient data is number, so it does not make sense for have this. Let me show for comparison. Here is we have something like frequency frequency of occurring some values within our group A and B. And here is, so it's chart made in correct way, but of course in this case it's provide not much information because what we can maximum measure, it's some identify some maximum or so. Anyway, it's correct approach to build such chart for such data. That's again, there I have spoken about visualization of data. In case if we have independent, because our independent variable is nominal, In case if we have no matter the same numbers, but our independent variables is continuous or discrete, so it will be correct of having something like okay, scatter plot, not two-dimensional. Yeah, scatter plot with line or just with dots. So this way I visualize my data set, and it's actually correct way do it per data set. Of course, I can try to do it this way. Technically, I can do it, but every time we have keep in mind, does it make sense? Does it make sense? Because in this case, we will have something completely different. Here is I visualize my data set A two time. Here is I got a relationship between A and B. It's not visualization A and B in total. It's simply relationship between these two variables. Probably it's not data visualization chart in this case. So in fact, right now I will delete it to not obscure us. And if I want to visualize both of these variables in the same chart, again, it makes sense only if we have the same scale and if it's generally comparable. I can add yet another data series. I can add yet another data series like this. Again, X volume. X volume. And Y values. So here is, okay. So here is now I have correct visualization of our discrete data set with XY scatter plot and two data series like this, two data series. And in case if I want to visualize statistical characteristics of this data, so of course I can't get statistics for nominal variables. It does not make sense. No, technically it will work, but it does not make sense at all. But definitely, if I want to summarize some data obtained from this patient, I can, and I have to apply descriptive statistics for this case. For example, in case of visualization, I can insert, where is my, um, uh, sorry, here is, almost forget. So here is, I can add the box plot, for example, for one data series, or better to do it for two data series. Okay, let's me do it for, I want to compare is that we have some difference between these measures for these two groups. Okay, in this case, I can use box plot. I can add the data labels, for example, and here is I will see. So here is I have median, I have interquartile range of our groups. I can see outliers. I can make assumption about some difference between averages in these groups. Of course, I have to prove this, and it will be goal of statistical further hypothesis testing. But this visualization give me some insight about potential difference. Same way I can draw, for example, histogram to make assumption about potential distribution type. Actually, characteristics of Excel histogram a little bit poor. We need to adjust from data series. We can adjust. No, format axis. We can adjust bins by category. We can adjust, no, here is we have independent category, so it does not work. For example, we can make our bin like 10 items and what more clear visualization about how many. Again, this configuration of axis will be depend about what those axes represent. If it's patient number, in this case, it will be not patient number, but that vital characteristic. So we should, at least we must know some minimum, expected minimum and maximum, and give settings for our bin relatively to this case. And only this we will have something like useful. And finally, could we use same techniques with a case when we have purely independent variable continuous or discrete in this case? Technically, yes, we can build the same chart here and we will get the same result. The problem is, does it make sense? Does it make sense in this case? Because if we measure in this case, made observation for a single patient, so we will, or two patients in this case, patient A and B, the same scatter plot will show for us only difference between these two patients, and it's obvious we have two persons, they are different, they are not the same humankinds. There is no proof that they are different. Would you try to reach me? No, not now. Okay, so again, we have to every time make sense, is we have to thinking about does that make sense also. Okay, let's move. We have only. Let's move forward. Move forward with. So I already spoken about frequencies, and what is outcome of frequency is frequency distribution of statistical data set. It's list of functions showing all possible values around the data and how often they occur. So, and here's number of some specific distribution, and especially we consider normal distribution. Actually, normal distributions show some similarity in our data set and depict some specific characteristics of it. Let's say specific features of normal distribution. Symmetric bell-shaped curve, then we have 50% scores lie above and below midpoint, asymmetric asymptotic to the x-axis, same mean median mode located at the midpoint of x-axis, and so on. And so-called 3 sigma rule, when deviation of when standard deviation fall under this rule. So here is we have this things in picture. So we have 68% in red, 95 in green, and 99.7 in red. So here is shown how our data frequency, again, not our data, but frequency have to be distributed. In this case, why it's so important to determine is it our data normally distributed or not? Because every time actually all statistical methods divided in two groups. So-called parametrical statistics, which could be upward for data which is normally distributed, and non-parametrical statistics, which have to be upward for those data which are not normally distributed, or to variables which are not discrete, nominal or ordinal. Here is important point. So we use non-parametric statistics for non-normal distributed data or nominal ordinal data. Other case, we use parametric statistics. In reality, our data set will be got some skew, so median will not equal to mean, and we have something like this. So again, having some value of mean and median, we made even not without seeing our chart, we can make some assumption about what our data already is. So, okay, I already shown this chart. Now move into our main question about hypothesis testing. So actually, statistical hypothesis testing forms statistical inference that use data from sample to draw conclusion about population parameters or population probability distribution. When we collect data from our experiment, we calculate descriptive statistics, and then we use those descriptive statistics data to make our assumption about general population that our data had been obtained from. And here is two kinds of assumption. First of all, about population parameters. So if we have some kind of difference in our sample, we are going to prove that the same difference will be available in our population. It's not random changes. And again, if we have normal distribution in our data, we can make assumptions that we have same distribution in our population. So again, we analysts test an assumption regarding population parameters. And again, as I said, that's methodology employed by analysts could be depend nature of data and usage reason for the analysis. So again, every time from one side we have relatively strict rules in usage of parameters, but which one parameters has to be chosen, it's very often not easy to be to determine. So when we have to choose, and in a few minutes, I will show how many different statistical hypothesis methods are available. So, but right before, we have to identify some chains of reasoning for inferential statistics. Like we should identify, is it our sample population distributed normally or not? Is it randomly selection? Is it we have sample estimate compared to underlying distribution, the same sign sample distribution, probability that sample estimate reflects population parameters, and so on. And in case if we have interval ratio data, we have to use n normal distribution, of course. We could use like parametrics methods, some test statistics, correlation, ANOVA, regressional analysis, and so on. The nominal ordinal data will use difference in proportion, chi-square, related measures of association, so general difference in the method. If we will try to bring some order and some structure in our hypothesis testing process, so here is again some simplified algorithm, very simplified, very general algorithms from 4 steps. First of all, we have to look at the data and decide about statistical general model. That's this first step. That's most likely for me. It's because it's actually most difficult things. We should just make some assumption only by having data, or again, we could, at this first point, we can already calculate some descriptive statistics to get our assumption, to make our assumption a little bit more easy. So here is, we have this. Then here is, in this case, we made, of course, we by it's the first step. If we will made draw histogram and draw box whiskey plot, we will make very clear assumption about potential, if we have normal distribution type or not. And as a result, we will be able to make choice between parametric, non-parametric statistical methods. Then, state null and alternative hypothesis. Yeah, at this point, we made 2 assumptions, one counter another about our potential outcome. More about this in a minute. Third, again, look at the data and decide and interpret statistical tests. So actually, if you have not complete descriptive statistics at stage 1, it's time to do it there at stage 3, or actually extend it to really get proof that our data normally distributed and so on. Then choose method, compute statistical tests, look at p-value, and depending to what do we have, is it our statistical value smaller than so-called significance level, so-called alpha level, which is margin of error. We can then again, we compare with some critical value and reject or accept null hypothesis. And if our significance is exceed our alpha level or our margin of errors, we just can't make a strict conclusion. We file reject null hypothesis, we file to accept alternative, and we just report our study and nothing more. So it's very unfortunate outcome, but in reality it's happened relatively often. So not all scientific results going into success, and very often we have something like this. Now, bring a little bit more order in this algorithm, get it more detailed, so how we can choose which method we have to use. First of all, we have in mind our data categorical or continuous. In case of categorical data, we have to compare proportion as it had been already spoken. So if we have two or more groups, we use, for example, chi-square test or other methods, because actually on the categorical data, a lot of different methods available. It's just there is no enough place there to put all them together. But in statistical textbooks, you can very easily find all necessary additional methods depicted in form of tables or such charts like this. In case of continuous data, again, it's all not fully completed driving. Depending to, we compare means or medians in group, how many groups we have. In case of two, we use, again, depending is the data normally distributed or not, we can use like parametric test statistics or not parametric Wilson test or something like this. For three or more groups, again, with normally or not normally distributed data, we could use analysis of variances or ANOVA or Kraskov-Waltz methods or something like this, again, because it's or non-parametric variances and so on. Actually, here is we have another representation of this algorithm in form of table. Again, it will be a little bit, this one table, it's a little bit shortened. It's just for educational purposes. More detailed version you can find in practical class materials, lecturing materials, and over internet you will have very, and even in this lecture I have more extended version of this chart. But anyway, this thing's very useful and we will apply it during classes. So this table has three processes from left to right. Left column represent some classes of practical tasks, depending on what you want to do, comparing control experimental samples, comparing sample data before and after experiment, comparing sample means to constant, our sample up to constant, and so on. Comparing some diffusion parameters, deviation of parameters into samples, and so on. So depending of how we formulate these tasks, how we imagine our goal of our analysis of our experiment, it's only pure theoretical things. It's things that a researcher have to understand by himself. Second column give for us useful statistical task to be done. Like if you talk about comparing control experimental sample, we compare independent sample means. If we compare sample before and after experiment, we compare dependent sample means. So it's just we simply have to know what we are dealing with. Like again, in this case I have already made. Here is if we talk about two independent samples, two different group of patient. So we will talk about compare independent sample mean. But if those observations had been made before and after experiment, they become dependent sample mean. It's not obvious from data. It's had to be known from your experiment design, from your workflow, from what you're actually going to do. And again, it's up to researcher. Third column give for us hints about what evaluation have to be done. Like in all cases, it will be checking distribution. In the case of control experimental sample mean, we have to add extra test for is it variances are equal or not equal. And then, depending to our answer of all this question, we have to get a single applicable test, single applicable method. So if you pass this table from left to right, you have to fall into single cell, which will depict method useful in your particular case. If you not made a mistake. But actually, it's not very difficult to make mistake in this case. Why it's so complicated? Because all this method not universal, and they have strict limitation on usage. From one side, from other side, that's our formulas. So with formulas and the data, you can every time calculate all this value. Just most of them will be useless. They will be useless until they fit into a correct combination of condition for usage. And here is major difficulties in statistical analysis. With modern software, it's easy to calculate all these parameters at once. The problem is to choose which one is correct in this case. And even modern artificial intelligence tool not exactly will assist you. Anyway, you can try ChatGPT, but you need to clearly describe what data for him, what data you have, what kind of condition you collect your data, what you are going to validate, what you're going to test, in order to retrieve some useful hint about what method will be useful in your case. I have tried already a few times, and it was results not all case will be very good, and it was very simple educational cases. Okay, now some technical details, which now much more easy. When we talk about state hypothesis, so we have to create two alternative statements. At the beginning, I signed at the beginning. So, and here is we have like blank points. We have to provide your statement. And usually they sound like in for null hypothesis, no difference between if we're talking about independent sample mean, it will be sample mean. If it will be dependent sample mean, it will be some standard, some variation. Okay, we put variation here and so on. But every time we have to extend null hypothesis with practical meanings, and it's pure again inference assumption of researcher. So if let's say independent sample means are equal. What does it mean in our practical case? What we are actually studying, what we are actually examining? Is it positive or negative case? It's answered only from statement of problem. Same, alternative hypothesis, there is present statistical significant difference between those statistical parameters. Again, we have added some practical meanings, what it will give for us, is it will be good or bad or so. Very difficult, really very difficult case, very difficult things in reality. Rejection criteria, so usually so-called alpha level or a point of rejection now is also critical value, and we start for medical biological researchers with maximum 5%, but usually in modern time we use even smaller alpha level, like 1 or even 1/10 of percent. So it's actually a number of cases which will fail, which allowed to fail in our investigation. 0.05 means 5%. So it means if in reality 5% of real outcome will not fit with our conclusion, which is okay, acceptable, more or less, depending to what we are talking about. Cancer treatment, it's excellent. Like some vaccination complication, very high, dangerously high. So again, it's not a constant, but we will use this value in our education case. So how we can mathematically, statistically clearly depict what is alpha level? So here is we have our null and alternative hypothesis inform that our mean equal to some given parameters, and alternative, that's our mean average lesser than given or greatest, because we can use here is we have left-tailed distribution. We can flip it right side and we will have right-tailed distribution. And here is we have area where we reject null hypothesis in favor to alternative, and how we calculate this critical value. In case if we have equal does not equal approach, so that same case where I'm talking that's the distribution parameters equal or not equal, or in this case it will be mean. We split our rejection area by 2 and we use left and right tail simultaneously to make conclusion. And all three cases altogether, one-tailed, left and right-tailed test versus two-tailed test, how do they can be depicted? So again, usually on classes we follow this pattern, but the same way we can implement left and right-tailed test. And here is we have, if we reject null hypothesis, we concluded that we have enough evidence to infer that alternative hypothesis is true. If we fail to reject, we conclude that there is no enough statistical evidence to infer that alternative hypothesis is true. Actually, it's also not proof that null hypothesis is true, unfortunately. But here is we have two false outcome, type 1, type 2 errors. So here is when if we reject or fail to reject null hypothesis, depending, so here is in gray we have correct outcome, and here is we have 2 points when we made a mistake, when we reject null hypothesis when it's true, and we fail to reject when it false. So how it can be seen with funny picture like this one, but in reality it's much more difficult to determine our cases. It's much very difficult usually, especially second error. So if type 1 error it's only happy if we reject null hypothesis and conclude there is something happened. Usually it's outcome of some incorrect measures. But with type 2 error, it's much more difficult to identify it. For example, difference is so small and is difficult to detect it. Difference big enough, but sample size not adequate or not representative. So as a result, we can got into these things very easily, and it's happened from time to time, especially for not for like treatment of some kind of rare diseases, when really we have very small, not sample, but population is very small, and here is difficult to make conclusion. As I already said, we use significance level. We compare our significance level obtained from test to compare with alpha level and make conclusions there. And if our significance level less than 5, our result is statistically significant. If it's exceed alpha level, it's not statistically significant. And actually here is we have this grades show for us is that we have significant evidence, weak evidence, or no evidence at all. Just keep in mind, if we have very small significance, we are also at risk of overfitting our data, and it's also a little bit suspicious. And finally, before we have a few minutes for our lecture, so what is automation? How spreadsheet could help us? Actually, it could help with calculation. But all this analysis, it's up to research. Or, okay, right now researchers' capabilities could be augmented by some language models, artificial intelligence assistant, and so on. But again, really they up to research. That's the goal of research. With analysis toolpack, we can calculate some predefined statistical tests. Yeah, we can do it. We can do it like descriptive statistics or some parametric, non-parametric statistics, and so on. So here is listed a few of hypothesis testing methods which is useful. All these parametrics. There is no non-parametrics methods on the analysis toolpack. They could be implemented in spreadsheet via formulas, no problem, but they are just not automated, at least in built-in analysis toolpack. Available third-party tool which is compatible with Excel or OpenCalc or Google Spreadsheet, and you can get more statistics there. And here is we have like example I very like to show every time. So here is as everything here. Yeah, so here is we have we are going to show is that we have difference for input parameters for male and female. We have some hemoglobin erythrocyte collected. So first of all, if we have again, we have different patient. It's categorical, nominal data set. Our data collected definitely discrete. And in this case, if you follow that pattern that I depict with a table, if one compare, for example, hemoglobin or erythrocytes for male, female, so it will be compare independent sample mean. Next step, we have to calculate descriptive statistics and determine distribution type. Is it normal or abnormal? Of course, we have. I will show this in details more during practices. Right now, I can only say that our values relatively low definitely fall under critical for skewness kurtosis. It's not very strong way to check distribution type, but it's easiest in spreadsheet. So we can assume our data normally distributed. As a result, we can use parametric method or test statistics. But in case of compare control and experimental sample, we have made additional test for Fisher test to prove that variances are equal or not statistically, not numerically. And after that, we can start with test statistics. So both tools are available under analysis toolbar. And here is we have results of this. So how to analyze this data? We have variance test, first of all. We have calculated variance. We have Fisher test. So assumption for variances, null hypothesis, variance statistically equal. Alternative, variance statistically does not equal. In this case, F calculated less than F critical. So it's look like our variance is statistically equal, but significance is 45%, way above 5% alpha level. So we can't make conclusion that our variance is equal or does not equal. We can use any of this method, but there is no evidence that variance is statistically equal. Again, we can't compare arithmetical value. It does not work. Okay, let's proceed with test statistics in this case. As previous tests not give us exact answer which one, so as researcher I decide to sample some equal variance. Again, our arithmetical value of means definitely different, but we don't know this for sure for statistics. So what do we get? Null assumption, null hypothesis, it's spoken, there is no difference between means, and practically it doesn't mean in this kind of questions that there is no difference between blood parameters for male and female. Alternative hypothesis spoken that there is present significant difference between mean, and it means that in our statement of task that blood parameters depend to gender. So we compare equal does not equal case for null hypothesis. So we will have to split our rejection area by 2, like shown in this chart. But all these things Excel do for you, for ourselves, it's just for visualization purpose given these things here. So here is we have test statistics. We have to use T critical to tail it and P significance to tail it. Our test statistics greater than T critical to tail it, so it's look like that we have to reject null hypothesis and forward to alternative. And let's check significance. This one is very small, significantly smaller than alpha level. So our evidence are enough. Our evidence are enough. And here is show how it's look like on this chart. Where is all these things in this chart? So finally, we have to reject null hypothesis and follow alternative, and which spoken that there is present significant difference in means and root parameters depend together. Okay, in fact, we already at the end of the lecture. We reach out of time. Thank you for your attention. And that's all that I can show for you today. We will continue next time with some other methods.